Good afternoon, all of you. For today's second session, we are pleased to have Dr. Vivek Venkataraman, sir, Associate Professor from IIT Delhi. Good afternoon, sir. A very warm welcome to AICT sponsored Atal FDP on emerging frontiers in quantum technology and communication. Thank you for joining us. It is my great privilege and honor to introduce today's distinguished speaker, Dr. Vivek sir, an eminent expert in the field of quantum communication system. Dr. Vivek Venkataraman is currently an associate professor in the Department of Electrical Engineering at IIT Delhi with a joint appointment in the Department of Physics. He completed his BTech in 2006 from IIT Delhi, followed by Master MS and PhD from Cornell University in 2012. He was a postdoctoral fellow and research associate at Harvard University until 2017 before joining IIT Delhi. His research interests and expertise lies in the area of quantum and nonlinear optics, light matter interactions and atomic physics, fiber optics, and integrated photonics, all optical devices, and novel light sources, optical signal processing, and communications. Respected sir, participants are looking forward to your talk. So, may I request you to please start your talk?
Thank you, Dr. Mukesh, for the invitation. I hope everyone can hear me clearly and also see the slides.
Yes, sir.
Okay. So let's keep it interactive. So please stop me at any point whenever you have any question or doubt. Please stop me and let's try to go slow through the material and try to understand rather than sort of discovering a lot of things. So please uh, do stop me and ask questions at any point. Um, so today I'll be sort of focusing on trying to develop the infrastructure for quantum communication over the existing sort of telecom infrastructure that we already have, and this fiber optic network that we use every day to access the internet, right? So sort of developing the infrastructure so that we can do quantum communications over the same already existing infrastructure so that we don't have to build new networks for this. Okay. So that would be my focus. So this picture sort of shows like this connected network where many users are sort of connected to each other, and we can build sort of quantum links between them. And these sort of colored balls are showing that they're sharing some quantum state uh, for this communication. Okay, so basically, first let's see what's the need for building this quantum infrastructure, right? So we know that our current communication systems work really well, and right, we are able to access so much data sitting anywhere in the world and able to do so many things. Uh, but one problem which is sort of coming up is the problem of security. Okay, so for example, when you use WhatsApp, you can see this this message that they show that your calls and chats are private. And how is it made private is that there is some encryption used. So instead of when you send a message directly sending the message of the text to the receiver, it is first encrypted into some other form such that it looks some jumbled garbage data. So anybody in the middle, if he tries to sort of intercept the data, then what they will get is some sort of looks like junk, unless they know how to decrypt it, right? And the same holds for any kind of secure transaction over the internet that we do. For example, when we access bank accounts, anything like that, right? So basically, the way sort of how security is implemented over the public networks nowadays is based on some mathematical technique, right? So one of the popular ones is this RSA. And so how it works is, for example, let's say I want to access my details of my bank account. So what I do is generates two prime numbers, okay, P1 and P2 on my computer. So these are some large prime numbers, let's say 100, 200 digit prime numbers, okay. And generating the prime numbers is very easy, okay. So like one can do it on your laptop. It doesn't take uh, a lot of resources. So you generate these two primes and then you multiply these two to get another large number n. Okay. So let's say these are 200 digit prime numbers, then the product will be some 200 digit number, some very large number. Okay. And then that number is sent over to the banks. Sorry. So that this n is sent over to the bank uh, server. And then the server of the bank uses this number to encrypt the data. So whatever your bank account details, etc., uh, that it is sent to you, that is first encrypted using this large number. Okay. So this large number n is also known as the public key because that is available over the public network. Okay. And but the encryption is done in such a way that if you want to decrypt it back to the data that you need these two prime numbers, P1 and P2. Okay, the original prime numbers, which is known as the private key because that's only available with you. So basically, anybody over the public network, even if they sort of hack into the data being sent by the bank, they won't know what the actual data is unless they can figure out what these prime numbers P1, P2 are. Okay, they only know the product here. So unless they can figure out the prime numbers, which are the factors of this n, they won't be able to decrypt. Whereas you, when you get the data, you are easily able to decrypt because you know these two prime numbers P1, P2. Okay. So there are certain, like for example, prime factorization is known to be a exponentially difficult problem in classical mathematics. Like there is no known algorithm, uh, no known efficient algorithm. So, for example, like basically the only thing which works is you have to search one by one through the numbers and see if they factor a particular given number or not. So basically, sort of the number of steps required typically scale exponentially with the number of digits in the number. Okay. So for example, if you have, let's say, a 500 digit number or a 1,000 digit number, to prime factorize that, you might need a supercomputer or, even some very large computing resources that are not really available to any normal person. Okay. So that's basically the networks rely on that, and then basically the secure transmission is done. But what is happening, is that quantum technology is being developed at a very fast pace, right? And quantum computers. So it's been shown that quantum computers, if we have a good enough quantum computer with enough number of qubits, which are error corrected and all that, then eventually this problem can be cracked. Okay, so you can prime factorize a very large number into its factors instead of taking exponential amount of time with the number of digits with any classical algorithm. You can actually do it with a polynomial, uh, like scaling with the number of digits. Okay, so you can dramatically reduce the time needed uh, to do this prime factorization, which means that now if quantum computers sort of become mature at certain stage, then people with access to quantum computers will be able to easily sort of break into your data and decrypt it. Okay. And there is already some progress being made. Like last year, for example, there is some Chinese group which already showed that one can break this sort of current cryptographic system which is used, but not for the current state of the art for this RSA system is 2048. So it's like 2000 bits. So this number n here is 2000 bits long. What the Chinese group showed was like up to like 50 or 100 bits they can do this factorization and decryption. Okay, because the quantum computers are not like the currently available quantum computers are not large enough. But eventually, one envisions that like within a decade or two, we'll have like quantum computers with thousands of qubits, and then one can sort of do this prime factorization and decryption. So then all our classical encryption techniques that we use for secure communication will break down. Okay. So that's why we need some other way, some new way to securely communicate over our communication networks. Okay. So thankfully, quantum physics, which provided the threat through quantum computers, also provides a solution. Okay. So again, like 30, 40 years back, people proposed that using quantum states, if one communicates using quantum states, then one can sort of come up with protocols which are physically secure. Okay. Physically secure means that, so what we discussed so far, the sort of classical security depends on some mathematically hard problem, right? And one can imagine that if you have enough resources, you can always solve that mathematically hard problem eventually very easily. But this uh, quantum communication actually relies on the laws of quantum physics itself. And it's physically secure, protected by the laws of physics. So there is, even if you have the world's most powerful technology or computers, you won't be able to break it because it's just physically secure. Okay. So this technique is not known as quantum key distribution. Okay. So we use quantum states of light uh, to sort of uh, generate a secret key between the two communicating parties, right? Which only they are able to. I mean, it's a secret key which only they can know. And any eavesdropper who tries to sort of eavesdrop on the quantum states being sent, just from the laws of physics, he won't be able to sort of. I mean, if he tries to eavesdrop, then the communicating parties come that there is somebody sort of intercepting the channel, and then they can sort of abort their communication and then start over again. Okay. And basically the important sort of properties of quantum physics that allow this is, one is the no cloning theorem. Okay. So which says that if I send some arbitrary quantum state over some channel, if somebody wants to sort of uh, copy that, so typically in classical communication, if I just send some classical bits, any eavesdropper can just detect those bits and then send those same bits forward again, right? So that can be done easily. And then so the communicating parties won't get to know anything happened because the eavesdropper is detecting and sending the same bits forward. But with these quantum states, what happens is that because of certain properties like superposition and then this collapse of the wave function during measurement, there is this property of no cloning, which means, yeah, an arbitrary quantum state, if it is sent, an eavesdropper cannot completely determine the state and copy it. Okay, so he won't be able to generate a copy to send forward. So if he does anything in the middle, the communicating parties will come to know. Okay, and then there is this property of entanglement. So quantum physics allows these special states called entangled states. So the state of two particles, right? So imagine one particle being sent to one of the communicating parties and the other one being sent to the other party. In this entangled state, sort of the two particles share correlations with each other. But if you ask what is the state of the individual particle, that is actually undefined. Okay. So, like in the first sort of title slide, I showed you this picture of sort of these balls which are changing colors between red and green, right? And it was sort of the two balls with the two people were always opposite color. If one was red, the other was green, and then it was randomly changing. But if you ask what is the color of one ball there, at any moment of time, you can't really say if it's red or green or anything. That's why I was showing it blinking. Okay, so it's not only that they share correlations, it's that if you ask what is the property of one of the particles, it's actually undefined. Okay. So that is really something which is not, I mean, goes against our classical common sense notions. But many experiments have shown that that's what it is. So basically, again, if an eavesdropper tries to know what the state of that particle is, so that he wants to get some information, he will basically get some random information which just looks like junk. There's no information there. because the information is in the correlations of the two particles. The individual particle has no information at all. Okay, so these sort of strange properties of quantum physics allow one to set up sort of a secure way of communicating that uh, that is physically secure and cannot be broken. Okay. So when we share quantum states, what do we mean by quantum states? Basically, the simplest quantum state is this qubit, right? Which you might have heard of. So in typically a classical bit consists of only like it can only have two states, either 0 or 1, whereas a qubit can have any possible state which is a superposition of these 0 and 1. Okay, so typically it's denoted in this unit sphere. It's known as a block sphere. So any point on this sphere is a valid qubit state. So you can see that there are infinitely many possible qubit states. Like for a classical bit, there are only two possible states, 0 and 1, but a qubit can have infinitely many possible states. And some of the important ones are shown here. So you have 0, 1 uh, corresponding to the classical bits, but you also have like 0 plus 1, an equal superposition of 0 and 1. Here 0 minus 1. So uh, there are phases which are important. So here you have 0 plus I. So another important thing in quantum physics is the use of complex numbers, right? So these complex numbers denote the phase difference between the 0 and 1 states. And basically, like using light or particles of light called photons, one can easily build a qubit using the polarization state. So the direction in which the electric field is oscillating. So we know light is an electromagnetic wave. And so the corresponding electric field in which direction it is oscillating, that can be used to encode the state of a qubit. Okay. So for example, if I take horizontally polarized light, which is so the electric field is oscillating in the horizontal direction, that I can denote to be the state 0. The vertical polarization I can denote to be the state 1, right? And then the superposition states will be some linear combination of these. So for example, if I take an equal combination of the horizontal and vertical, I will get the diagonal polarization oscillating at 45-degree to the x and y axis. That will denote this plus qubit state, which is a superposition state. And similarly, like an anti-diagonal state and things like that. Okay. And these ones, like the 0 plus I1, would be like the circular polarization states, left circular and right circular polarized. So using the polarization degree of freedom, it provides a natural sort of physical implementation for a qubit. And that is, of course, useful in quantum communication because we already know that for classical communication, right? For example, we send light over optical fibers to communicate, right? So again, we can use the sort of same infrastructure, but now instead of using classical bright light pulses, we have to use single photons, right? So one sort of standard protocols that one can use for this quantum communication is known as BBM 92. So this was proposed by three people, Bennett, Brassard, and Mermin in 1992. So here we use an entangled photon source. Okay. And one of the, again, as I said, entangled states are states of two particles. So here, this is a source which is generating two photons. One of them is sent to one of the communicating parties, the other one is sent to the other communicating party. And then each party measures the state of the photon. So it measures the polarization in any in any two bases. So again, bases means here diametrically opposite points on the sphere. Okay. So like your HV basis or the 0, 1 basis would be the North Pole and the South, right? That's one basis. Another basis would be, for example, your plus and minus states. So on the equator, diametrically opposite points on the equator. Any two diametrically opposite points on the sphere constitute a basis. Okay, so I can measure in any basis, and then the measurement outcome would be one of the two basis states. right? So that's a postulate of quantum mechanics. If I measure in some basis, then the outcome would be one of the two basis states. So for example, here, if the photon goes here, so here, so the photon comes, this is like a 50-50 beam splitter. So there is a 50% chance that it will go here, 50% chance it will go here. If it goes here, then this is known as, this element is a polarizing beam splitter, which means it separates the horizontal and vertical components. So for example, if the photon reflects off here and is detected by this detector, that means I measured the polarization V, the vertical polarization for the photon. Okay. If it if this detector clicks, that means I measured the horizontal polarization. So this is measuring in the HV basis. But let's say there's a 50% chance for the photon to go into the other path. Now in the other path, what I do is put a half what is known as a wave plate. Okay. A wave plate basically rotates the polarization. So basically, you can think of it as, so it rotates the polarization. A half wave plate rotates the polarization by sort of 90 degree on this sphere. So H polarization becomes D and V polarization becomes A. Okay. So by putting this wave plate, what I'm now doing is measuring in the dA basis. Okay. So if this detector clicks, for example, it's D, and if this detector clicks, the polarization measured was A. Similarly, on Bob's side, the other communicating party. So an entangled state would be looking something like this. Okay, so it's a two particle states, right? So one denotes the polarization of photon one, two denotes the polarization of photon two. So one of the possible entangled states is this state, for example, HH plus VV. So that means either the two photons have both horizontal polarization or the two photons have both vertical polarization. Okay. So you can see that I cannot write this state as a product of the state of photon 1 multiplied by another state of photon 2, right? It is what is known as a non-separable state. So entangled states are something which only have correlations between the two particles, but individually you cannot write the state. I mean, you cannot write the global state as the product of state 1 plus times the product of state 2. And now you can write this state in any base. So this was written in the HV basis again. I can also write the state in any other basis. So if I write the state in dA basis, then the state looks like this. Okay, so you can see that even in the dA basis, the two photons share correlations, like both will come out to be diagonal or both will come out to be anti-diagonal. So that's the key feature of entangled states, that in any basis you can write the state in any basis, and in any basis they will share correlations. Okay, so that's a particular quantum feature that is not really. I mean, there is no analogous classical analogy. Like you can share correlations classically, but this correlations being preserved under change of basis, that really doesn't have any classical counterpart, right? Like for example, I can take a box which has only red and black balls, let's say, and I randomly take out one red and one black ball and give one black ball to one party and the other red ball to the other party. Okay. Then also, when the two parties, uh, I mean, they say the result, they will find that always they have opposite. Like if one has red, the other will have black. One has black, the other will have red. Okay. But this is only in one property, color, right? If I try to measure some other property, the correlations will not be there, like in, let's say, size or shape or whatever. But here, basically, what is happening is no matter which basis I measure, the correlations are preserved. Okay, so for example, one can set up a protocol for quantum communication using such an entangled state. So what happens is that, so they independently measure which of the four detectors clicked for each photon they received. Okay, and since there are four detectors, you can denote 2 bits of information, two classical bits of information for every detection, right? So for example, if this detector clicked which denotes H, then I can denote the bits 0, 0. If this one clicked, I denote the bit 0, 1. If the D detector clicked, I say 1, 0, and if the A detector clicked, 1, 1. Okay. So Alice gets a series of detections. So let's say first photon she detected was D, then A, H, V. She gets some sequence of detections. On the other end, Bob also gets some series of detections. Okay, and they denote they generate this bit string by denoting the corresponding classical bits for the detections. Okay, so D is denoted as 1, 0, A is denoted as 1, 1, H is denoted as 0, 0, and V is denoted as 0, 1. Okay, and now what they do is they take a subset of their measurements and then share the first bit. Okay, so they see if the first bit of their measurements whether they were the same or not. Okay, so for example, for this first measurement, so Alice got D, but Bob got V. So Alice's first bit was 1, Bob's first bit was 0. Okay, so here it's different, so they just discard, ignore this. For the second one, both got A. I mean, so they don't know that yet, but so if they share the first bit, so here Alice's first bit is 1, Bob's first bit is also 1. Okay. So now if they see that their first bit is the same, then they keep the second bit as the secret key. Okay. And why do they do that? Because again, if you go back to the state here, right? The state here is if whatever the two measurements has to be the same, right? So for example, here in the DA basis, either both will get D or both will get A. Okay. So if they measure in the same basis, right? So here they've both measured in the DA basis and both have got A. So the first bit denotes basically which basis they are measuring in, whether this set of detectors clicked or this set of detectors clicked. That's what the first bit is denoting, right? So if the first bit is the same, then they know that the second bit has to be the same because of the state. Okay. So they can just keep the second bit as the secret key without even confirming that it is the same. If they just check whether the first bit was the same and then keep the second bit as the bit for the secret key. Okay, so that's what they do over a series of bits. You can see. So again here, so if they both measure in different bases, then of course they will get different results. But if they measure in the same basis, either DA or HV, they will get the same result. Okay, so from the first bit, they can check which of like on which times did they detect in the same basis, and for that they can keep the result as the secret key. And this second bit nobody knows, right? Only they know what the result was. And because of this entangled state, they are sure that their result will be the same as the other ones. Okay, so because of these correlations, one can set up this secret key, which only is being generated once the measurement has been made at the two ends, two communicating party ends. Okay. So again, if one does some funny business in the middle here in the channel uh, where when the photons are being sent, then Alice and Bob will find out that these correlations break down. Right? So they will see that when, for example, they will see some cases where the first bit was the same, but the second bit doesn't come out to be the same. So they will find out somebody did some, uh, so somebody tried to hack in the middle. Okay. So this protocol is fine, but of course it is also again limited by losses, right? So if you are sending photons, now remember we are sending single photons, right? Instead of classical light pulses. So losses are a big problem. So even fibers, although they have very low losses, once you go to tens or hundreds of kilometers, then the losses are not negligible, right? So you can lose quite a large fraction of your photons. So to extend the communication distance and set up like a uh, proper network of nodes, you need these quantum repeaters. Just like in classical optical communication, we have optical amplifiers, right? So every like 50 or 80 kilometers, what is done is that the light is amplified again to a higher level to compensate for the losses in transmission. Similarly, we need something here to compensate for the photon loss. So what is done is we need basically periodically we need to have these nodes which can sort of couple uh, successive links which have their own entangled photon sources. Okay, so let's say each entangled photon source, let's say there is some limitation on the link length, which is based on the losses in the channel, right? I can now use two such links, right, and double the communication channel by using this quantum repeater in the middle. Okay, so what is done here is you can see one of the photons from each entangled photon source is sort of interfered on a beam splitter here in this repeater node, and the other photon from each source is sent to the communicating parties. Okay, so now you can see these two photons are entangled, and similarly these two photons are entangled, right? And but like these communicating parties, Alice and Bob, the photons they are getting were not initially entangled. They came from different sources. But what one can do is do a special type of measurement here in the middle, which is called a Bell state measurement. Okay, it's basically some interference between these two photons, which then projects these two photons, the other two photons, into an entangled state. Okay, so basically, instead of directly sending an entangled state between the communicating parties, now what we've done is broken the link into two halves, right? And then because of this interference in the middle, we can sort of double the effective distance over which we have communicated. So this particular interference here, this is known as entanglement swapping, because basically you can see, so initially these two photons were entangled and these two photons were entangled. And finally, after this measurement, we have transferred the entanglement over to this other two photons, right, which were not initially entangled. So that's why it's called entanglement swapping. But to do this practically, you need certain properties of the photons, right? So for this interference to happen in the node here, the photons coming from these two sources need to be identical. So they need to have the same frequency, wavelength, bandwidth, polarization, everything, right? Only then they will interfere and give you this functionality. So when we build sources here, we need to make sure that we can build sources which give identical photons. And then the other thing we need are these quantum memories. Okay. So again, for them to interfere, they need to arrive at the same time. Okay. So one can imagine, depending on where these are physically placed, maybe the time of travel from here to here and here to here, or the time at which the photon is generated here is not exactly the same at which it is generated here. So a priori, they might not arrive at the same time here on the beam splitter for interference, right? So we need to be able to delay or store photons in the paths for some amount of time. So just like a classical memory where we can store some bits in memory, right, and then later retrieve it, we need a quantum memory where we can store these qubits and then later release or delay them by however much we want. And so typically these quantum memories they are developed they are based on some atomic system. Okay, and typically the photons that can be stored in these atomic systems are uh, in the visible to near infrared range. So sort of towards the red, like 600, 700 nanometers wavelength, or up to maybe 800, 900, 1 micron wavelength, right? Whereas the wavelengths that that we use in optical fiber communication are typically longer wavelength, like 1.3 to 1.6 micron in the infrared. But for these quantum memories, typically most of which that have been developed so far, uh, the transitions lie in the visible and near infrared regions. So that's something to keep in mind. Okay, so that's sort of just a summary of the quantum communication system and protocol. And then we want to build such systems over the existing telecom infrastructure, right? So we know that the classical, I mean, whatever communication we do nowadays, the classical telecom systems, they're based on digital logic, right? So uh, any information like video or audio starts from some analog signal. Any real signal is analog. Then it is converted. We do this analog to digital conversion, right? And ultimately send binary data, right? And this is done because it can give us a lot of advantage over directly sending this analog signal in terms of immunity to noise, and then we can build error correcting codes, right? And then also for memory and other techniques. So this digital communication infrastructure has been set up over the last 40, 50 years, and it works really well, right? Uh, I mean, to give you some idea, like when you use your cell phone, the amount of power that your cell phone is receiving, let's say for a voice call or something, it's in the range of picowatts, 10 to the minus 12 watts. Okay. But even with such a small amount of signal, we can talk with each other with high fidelity and low noise, etc. Okay. So this technology is really well developed. And we know about these various generations, like with years, like the capacity keeps increasing, and people are already talking about 6G now. And for 6G, people want to integrate the quantum systems into the classical telecom uh, infrastructure also. Okay, so over short ranges, like for example, within a city, or we use these mobile like microwave or RF waves, right? Uh, which are sent through antennas on towers. But if you want to go longer distance, then we have to go to optical fibers, right? Because again, the losses provided by optical fibers are much lower than, for example, the free space losses for microwaves. So typically for long distance transmission, everything is converted to an optical signal and then sent over optical fibers. And these optical fibers are now laid out all over the globe, right? So this shows the national knowledge network, the fiber network within India, and then over the globe, like there are these undersea submarine cables laid down, which connect different continents. Okay, so basically, this optical fiber infrastructure has enabled global connectivity, and now like anybody can access the internet and instantly get any information they want sitting anywhere in the world, right? So it's a really uh, remarkable development which has happened over the last 30, 40 years. And this sort of shows the growth in the data traffic over the internet. Uh, and now we are talking about, so you can see the data, the numbers here in hundreds of exabytes per month. And exabyte is 10 to the 18 bytes. Okay, so we are talking about 10 to the 20 bytes of data being sort of generated and sent over the internet every month. And most of this is now driven by smartphones. You can see here. Okay, so I mean, a lot of this data might be just Instagram reels or Netflix movies, or might not be actually in the end something which is useful to humanity, but that's a different question altogether. But this telecom infrastructure, you can see, is sort of keeps growing at an exponential rate, and basically the next phase is to integrate quantum communication over this infrastructure. Okay. So now, if we want to do this quantum communication over the uh, optical fiber infrastructure that we already have, so again, we have to use wavelengths which uh, sort of accrue minimum loss, right? So again, we are talking about wavelengths in this range, sort of 1550, is the wavelength with the lowest loss. And then there's this range of wavelengths, let's say between 1.3 and 1.7 micron, which has sort of fairly low loss. Okay. So if we want to do quantum communication using photons, we have to use photons of this wavelength. if you want to use the existing telecom infrastructure. And then already there has been some efforts towards this. So people have gone up to like 500 kilometers for quantum key distribution. Okay. And the advantage is again that we have all this existing infrastructure which is developed over last 40, 50 years, right? So we don't want to build another new entire thing for the quantum communication. If we can use the existing infrastructure, then that would be the sort of most cost effective and a practical way of moving forward. And we can also take advantage of these technologies like electro-optic modulation, so electrical to optical conversion and back, and then WDM, like wavelength division multiplexing, where we send data over multiple wavelength channels parallelly through the same fiber, right? These kind of technologies we can take advantage of. So now basically I'll move on to some of the work that we are doing towards developing this infrastructure. Okay, so I'll talk about two sort of major thrusts that we are looking at. One is sort of using this WDM technology, right, to connect multiple users over a quantum communication link, right? So again, ultimately moving forward, we would want like lots of users, just like we have for the right now when we access the internet, multiple users can connect simultaneously and right, multiple users can access simultaneously. So we want to do something similar for the quantum communication networks. So far, most of the demonstrations have shown point to point, like only two parties communicating with each other. But we want to develop something where we can extend it to multi-users. Okay. And then the other part is to sort of miniaturize the components. So moving towards chip scale uh, photon sources such that many of these can be integrated in a small form factor. Again, when we want to build a large network with many nodes, then we want the components to be very small, just like now we have electronic ICs with a lot of components integrated on a small chip. Similarly, we want to do for this quantum photonics also. Okay, so we'll start with this one. These are some publications that you can look at if you're interested in further details. Okay, so now basically the workhorse is to generate these entangled photon pairs, right? To do any quantum communication, we have to generate these entangled photon pairs. And so we need some special materials to do this. Okay. So these special materials are called nonlinear materials, where the optical response of the material is nonlinear. Okay. So we don't need to go into too much details right now, but I mean, if people have questions, we can go into that. So here, basically, we use a material which is called PPLN. So LN stands for lithium niobate. So that's a material which is made out of lithium niobium and oxygen, lithium niobate. It is a nonlinear material, and PP stands for periodic polling. So we'll see what that means. Okay. So what it means is that if I send in some laser light at a particular frequency, okay, into this lithium niobate material, because of its nonlinear nature, what happens is that this photons from this input laser, which is called the pump, it can actually split into two photons of lower energy. Okay, they are called signal and idler. And this comes basically from the nonlinear optical effect. So, because I mean, energy conservation has to hold, so the frequency or the energies of the two output photons have to add up to my input pump photon. And momentum also has to be conserved. So, momentum for light translates to the wave vector. Okay, so that wave vectors also have to add. So, this wave vector for the signal and idler have to add up to the pump. Okay. But typically, that is difficult to satisfy in the material naturally because this wave vector depends on the refractive index of the medium. Okay, so the refractive index typically is a function of the frequency or wavelength. So, for example, the refractive index at the pump wavelength will be different from the refractive index at the signal and idler wavelengths. And if you look carefully, like to do this conservation of uh, momentum here. So if I want Kp to be equal to Ks plus Ki, then the refractive index at the pump, signal, and idler all have to be the same, which typically is not possible in any material in general. Okay, so there is some phase mismatch here, which is the difference in the wave vectors delta k. And what is done is we what is known as periodic polling. So there is some crystal arrangement of the lattice here of the this lithium, niobium, and oxygen atoms. Okay, so there is some periodic arrangement here which we denote by this arrow. So what we do is periodically flip the domains. Okay, so we sort of flip the arrangement of the atoms, and this can be done by applying a large electric field. And we do this with a certain period. Okay, so you can see this period lambda, and then the domains keep switching back and forth, up and down. So this, you can think of it as a grating within the material, right? And this grating provides an extra wave vector. So for those of you who might be familiar with the term Bragg scattering, like whenever you have a grating and you incident some light on it, the light gets scattered. And because of this extra grating structure, it can compensate for this momentum mismatch between the signal and idler. Okay, so that's why this periodic polling is done. So basically, after this periodic polling, this material is referred to as PPLN, periodically poured lithium niobate. Anyway, so this technology is now well developed, and you can buy these periodically poured PPLN crystals and waveguides commercially. Okay, and then this process happens for a particular combination of the polarization. Again, we said that the light can be polarized. Polarization means the direction of the electric field uh, corresponding to this electromagnetic wave. So this process happens for a particular combination of polarization. So, for example, for this case, this is pump, signal, and idler are all vertically polarized. So the electric field here points in the vertical direction, and similarly for these signal and idler photons also. Okay. So this process is known as spontaneous parametric down conversion because uh, I mean the pump is getting down converted to lower frequencies, the signal and idler. Anyway, so basically one can, as I said now, commercially get these periodically pulled lithium niobate. So you can also sort of form them into waveguides. So so this is box contains this PPLN waveguide. You can see that the waveguide looks like this, and it guides light within this waveguide. And if you again incident pump, so laser light at this particular pump frequency, which is corresponds to a wavelength 775 nanometer in our case, then it can generate signal and idler photons at half the frequency, right, or twice the wavelength of the input pump. So here the photons are generated at 1550 nanometer, which is the telecom wavelength. Okay. And then you have to maintain a particular temperature for this waveguide for this process to happen, etc. Okay. So now, okay, so this generates pairs of photon signal and idler, right? So that's one thing that we need pairs of photons, right? We need to send one to one party, the other to the other party. But we also need to generate this entangled state, right? The state which has correlations between the two photons. So how do we do that? We do that by putting the waveguide in this sort of Sagnac, so-called Sagnac loop. So we put it in a fiber loop where we have the pump laser coming in from here, okay, and then we have this loop. So the pump laser splits into two paths. One is going clockwise, the other is going anti-clockwise. So you can imagine half the pump power is going clockwise, half the pump power is going anti-clockwise. Okay. And this element here is a polarizing fiber polarizing beam splitter. So which means that it splits, the two paths have uh, two different polarizations. So the vertical polarization goes here, the horizontal polarization goes here. Okay. And remember, we said that the down conversion process, so the signal and idler generation from the pump happens for this vertical polarization. Okay. So from here, like in this direction, when the pump enters the waveguide, it generates vertical polarized signal and idler photons in this direction. Okay. And in the opposite direction now, it is horizontally polarized. So first we do a 90-degree twist in the fiber to make it vertically polarized because again, we want vertical polarization. And so after this twist, now vertical polarization is going entering in the anti-clockwise direction also, and that generates uh, its own signal and idle photons vertically polarized in this direction. Okay, so now these ones come out again from here like that. The clockwise ones first they go through this 90-degree twist. So again they become from vertical they become horizontal and then they come out. Okay, so now these two paths interfere, right? Or when the photons come out here, after coming out, there is an equal probability that they came from this side or they came from this side. Okay. So the state coming out can be written as this sort of entangled state. So if they came out in this path from this path, then they're VV. If they came out from this path, then they would have become HH, right? But once they come out here, there is no way to know like which path they were originally generated from. Okay. So basically, the state coming out here can be written in this entangled state. So this doing this nonlinear optical process in this sort of loop configuration enables me to generate this entangled state that I want. Okay. And now once the photons come out, then I can do various measurements to characterize the source, right? So I can put sort of filters at different wavelengths and then see how many photons are coming out to see sort of or over which wavelengths this generation is happening. Or here I can split the two photons, right? And according to wavelength, and then see when I get one photon here and one photon here. So coincidence detection. So that will tell me how good the uh, entangled photon state being generated is. So for example, here, if we scan the wavelength, we take a filter and just scan the wavelength and see at each wavelength how many photons are coming out. Then we see this sort of spectrum. So it's centered at 1550. And then there is a bandwidth. And here the bandwidth is quite large. So you can see it's about 50 nanometers. So all the way almost from like 1520 to 1570, 1580. Over this entire range, photons are being generated. Okay. And then we also measure these coincidences. So coincidences tell you that, I mean, the two photons are coming out at the same time because they're being generated together. And as we increase the pump power, so as we increase the pump input pump laser, more and more photons are being generated. So you see the coincidences going up. And we also see accidental coincidences. So accidental coincidences are uh, what are the counts when there is some delay between these two arms. So those are some spurious photons which are being generated through some other process. So we don't want these accidental counts. We only want these coincidence counts. But we do see some accidental counts. And the ratio between these two tells us how good our entangled photon source is. So this coincidence to accidental ratio car that tells you how good your source is. So you can see that um, we get this coincident to accidental ratio in many hundreds, like above 100 over this entire range. So that means 99% or 99.9% of the time, the photons being generated are coming together in this entangled state. So that means that the source is very nice. And we can also see, we also characterize how many photons are coming out, sort of the rate of photon generation per second per unit bandwidth per unit pump power. Okay. So the higher this rate, the more photons we can send to the communicating parties to increase the rate of this secret key generation. Okay, so now we also have to characterize the uh, so because of this broad bandwidth, right? What we can do is separate the photons into different channels, right? And then do this wavelength division multiplexing, which is you like a standard thing that is done in classical optical communications. So different data is put parallelly on multiple wavelength channels and they're sent together on the same fiber. So we can also do the same thing here. So we can separate the photons into different channels. And we know that so the my, like for example the two red bands here, right? Because we know that this pump frequency and the idler frequency have to add up to sorry, the signal frequency and the idler frequency have to add up to the pump frequency, right? So we'll have correlations between different wavelength channels, right? So the two red channels are correlated, the two green channels are correlated, the two blue channels will be correlated with each other, and similarly to gray channels. So symmetrically about the pump with equal detuning from so symmetrically about this 1550 nanometer we can at the same detuning we can select the channels, and we can do this using standard telecom equipment. So there is this for example component called arrayed waveguide grating, which basically splits the light into different wavelength channels, and these channels are as defined by the International Telecommunication Union. So it has specific wavelengths, and typically it has each channel has a bandwidth of zero point 0.8 nanometer or 100 gigahertz. Okay. So the broadband photons which are coming out from the source, we can channelize them into different channels, right? And each channel pair we can use for particular user pair for them to communicate, right? So all of them can communicate simultaneously using different wavelengths. And so this shows if we measure the sort of again coincidences between different channel pairs, you can see that each channel is correlated only with its corresponding channel on the other side. So yellow denotes high coincidences, blue denotes no coincidences. So you can see that. So for example, channel 35 is only correlated with channel 34, and 36 is only correlated with 33. Okay. So this shows that we have very good correlation in the respective channels. And then to characterize to show actually that we are getting entangled states which we can use for quantum communication, we have to do certain measurements. So one is this Bell's inequality test. So we measure the two photons in different bases, again, like along different directions in that block sphere, right? Which we can do again using these half wave plates and polarizing beam splitters that we had discussed. So you measure the two photons in different basis settings with certain along different angles of measurements basically, and then you compute this correlation coefficient and this Bell's parameter, okay, this S. So you do a series of measurements in different bases, and then you compute this Bell's parameter S. And if you have an entangled state, then this S parameter should come out to be more than 2. Okay. So that's a experimental experimentally robust way of showing that you have entangled states. This was first proposed by Bell and then implemented by other people. And basically, the Nobel Prize in 2022 was given to people who first sort of experimentally verified this. And then there are other measurements that one can do. So, for example, quantum state tomography, which is again similar, like you measure the two photons in different bases. Now you have to do like more measurements. So here you need 4 different basis settings. For this, you need like 16 different basis settings. But the idea is the same. You measure the coincidences with different basis settings, and then you build up this what is known as the density matrix of the state. And then you can compute the fidelity, which is telling you how close your generated state is to the ideal entangled state. Okay. So again, like there's this measure, if the fidelity comes out to be greater than 1 over square root 2 of, or roughly 70%, then you have and like true quantum state and entangled state, which cannot be classically described. So we do these sort of measurements on our source. And so the measurements look like this. So the red curve, for example, we have a half wave plate on. So if I go back here, so this is sort of the setup, right? So you have some wave plates here, followed by a polarizing beam splitter. So you set different settings. So you rotate these wave plates by different angles, and then you do the measurement. Okay. So the curves here are, you fix the angle on one of the wave plates, and then you rotate the other wave plate through this angle, so 0 to 90 degree. So you can see this, you get this sort of visibility curve. So for certain set of angles, you get high coincidences. For another set of angles, you get low coincidence. And then you can shift the setting of the wave plate on the other party, and then again repeat the measurement. You will see that these curves will shift. Okay. And then the contrast that you get here between the maximum and minimum, that tells you how good your entangled state is. So basically, this is known as the visibility, the difference in the maximum and the minimum. And again, we can do this quantum state tomography also to find out how good the entangled state is compared to an ideal one. And we get up to like 95%. And not only that, we can also change the entangled state. So for example, here this one is generating HH plus VV. And just by changing the polarization setting, so for example, here we have a polarization controller. Okay. So by changing the setting of that polarization controller, we can change the entangled state to some other state. So here, for example, it becomes HH minus VV. Okay. Without losing the fidelity. You can see that still it's 95% as compared to an ideal entangled state. Okay. And then we also do this channelization into the different channels. And for each channel pair, we do these measurements and show that the fidelity remains very high, right? 90% or above. And this bell parameter, the S parameter that we said had to be more than 2, right? So it comes out, you can see all of them are much above 2. And so we show that for all the channel pairs, they are all in entangled states, and all of them can be used parallelly for multi-user quantum communication. And the measurements that we did were with sort of standard semiconductor-based single photon detectors. But nowadays you have these uh, much better performing superconducting nanowire-based single photon detectors. So if we use those detectors, then our results would be even better. So the 95% will even maybe go up to closer to 100%. And also the rates would be higher. Okay, so then again, to build a network, we also need to show that we can send these over long distances. So then we put fiber spools here, and we went up to 100-kilometer distance. And we characterized that, we showed that the entanglement remains. So the fidelity remains much above the minimum required for entanglement. And then we were also able to share a secret key with some rate here. So the rate you can see is not very high because again, because of the losses in the fiber. So again, for 100 kilometers, typically the loss becomes like more than 20 dB. So that's less than 1% transmission. So less than 1% of the photons you send are received. So that's why the rate goes down. But again, by using better detectors and uh, also better components, we have some insertion losses for all the components that we use. One can boost up the rate you can get uh, at least kilobits per second or maybe hundreds of kilobits per second. Okay, so we showed that this works in a lab setting. Then the next stage that we are now doing is to actually deploy, I mean, use this in a deployed fiber setting. So in our IIT campus, we have some deployed fiber. So we got access to one of these. So it's going from our lab to some other building and then coming back. So this is actual real fiber which is used to send all the classical data and all that. But this is of course not as good as the pure fibers that we are using in our lab. So the round trip loss here you can see is about 22 dB. Uh, but you want to see if we can still do the quantum communication over this real deployed link, and we showed that yes, we can. So the rates go down, but still we show that the entanglement is preserved, and we can get a low error rate. So this QBER stands for qubit quantum bit error rate. Uh, and so if it's shown that if it's less than 11%, then your quantum communication protocols can work. So we show that we can like be much below the 11% threshold, and all the entanglement metrics are still preserved. Okay. Of course, we want to improve things and now scale it up to sort of real world networks. So that's the next phase of the work. Uh, okay, so maybe I'll just take a break for 2 minutes. I'll be back and then start the second part of the talk.
Sure, sir.
So, be back. Yeah. Okay. So, are there any questions from the first part?
Audience, if you have any question, you can type your questions in chat box. Okay, I think. Sir, please continue.
Okay. So maybe in the end, we can discuss more. So the second part now deals with so these fiber-based, the PPL and waveguide-based sources, they're still sort of quite bulky. So each source is maybe looks like 10 centimeter by 10 centimeters, pretty big with fibers coming out. So if you want to scale this to uh, again many users, many nodes over a fully connected network, then eventually we want to miniaturize things, right? So this second effort that we have is to miniaturize these sources onto chip scale devices. Okay, so the idea is to again have your optical components like sources and then all the processing in a very small integrated photon integrated circuit, right? Which provide a lot of advantages over other sorts of platforms, like for example, room temperature operation. Photons don't interact with the environment much. We have multiple degrees of freedom that we can use, like frequency, wavelength, polarization, transverse mode, lot of degrees of freedom. So we basically want to, just like the electronics semiconductor industry developed over the last 50, 60 years, and for basically now they can put billions of transistors on a small chip. Basically, we want to go the same way for photonics and put a lot of these photonic components in a small chip. So these are some examples of efforts from abroad. Okay. So our focus is again to make these sort of quantum photonics light sources that we can use for QKD and other applications on a chip scale geometry. Okay. And one sort of natural choice of material would be silicon because, again, the entire electronics industry is based on silicon. So, this entire foundries, the CMOS nanofabrication facilities have been developed for silicon. So, if we can also uh, do our quantum photonics technology on silicon, then that would be the most, again, practical way of moving forward and scaling up. So if we want to generate again these kinds of entangled sources in silicon, so remember in the previous case the lithium niobate uh, that was what is known as the second order nonlinearity. So this term was contributing there, and there my like a single photon from my input pump laser was splitting into two smaller frequency photons. In silicon, it doesn't have this second order nonlinearity because that needs some special crystal structure. What it has is this third order nonlinearity. Okay. But we can use this third order nonlinearity also in a process called spontaneous four-way mixing. So that previous one in the lithium niobate was called spontaneous parametric down conversion. This one is called spontaneous four-way mixing. So here what happens is two photons from my pump laser are converted to two different photons now. But you can see, so now the signal and idler photons, one is slightly smaller than the pump and one is slightly larger than. Okay. So in the previous case, for the uh, in lithium niobate, the spontaneous parametric down conversion, the two generated photons roughly had half the frequency of my input pump photon. But here they roughly have the same one, like slightly larger and slightly smaller. Again, like energy and momentum conservation need to be satisfied. So we need to worry about this phase mismatch or the difference in the momentum. So now, since there are two pump photons, so the momentum conservation condition is now two times. So beta is same as like the wave vector that I talked about. Um, because now we are doing this in waveguides. Sometimes I mean, in the literature, the K is also denoted as beta, but this is basically the wave vector. So now you have two pump photons. So the input wave vector is two times the wave vector of the input laser, and then the output wave vector is the sum of the signal and the idlers. So beta s and beta I. So the difference in the input and output momentum is 2 beta p minus beta s minus beta I. And this is what we want to minimize or make it close to zero for the process to happen efficiently. So in that case, in the lithium niobate case, we had to do this periodic polling to satisfy that. Here, what we'll do is actually use the dispersion of the waveguide itself. So we'll be using very, very small waveguides because silicon, we'll see silicon has a refractive index which is much larger than the surrounding cladding, that is the silicon dioxide. We can make these waveguides really, really small. Okay, so sub micron dimensions. So these are called nano waveguides. And people are already using this. So, for example, there's this company in Canada, Xanadu, which is trying to make a all photonic quantum computer using this technology. So, the materials used in silicon, I mean, electronics, also which we also want to use in silicon photonics, are silicon, right, which has refractive index 3.4, silicon nitride, which has refractive index 2, and then silicon dioxide, which has refractive index 1.45. So because of this large index contrast, so like silicon is 3.4 and silicon dioxide is 1.4, you can make this core of the waveguide really small. So you can see here 400 nanometer, silicon nitride is 800 nanometer. And because of this strong confinement, what happens is, so two things. One is this, so the mode area here is really small, and the rate of generation of photons, right, that scales, of course, with the pump power and the length of the waveguide. But it also depends on this nonlinearity parameter here, gamma, which is inversely proportional to the effective mode area. So the stronger you confine the light to a smaller area, basically the intensity of every photon goes up, right? As you confine it to a smaller and smaller area, the intensity of the photon goes up, and so you get a stronger interaction. So by making these waveguides really small, we can make the interaction really strong. So and the other thing is that again, because of these waveguides being really small, they can have very strong dispersion. Dispersion means that like the refractive index or the effective refractive index or the wave vectors that uh, the photons see here can depend strongly on the wavelength. Okay, and that we can use to satisfy this phase matching condition. So then in the material itself, in the bulk material itself, it is difficult to satisfy this phase matching condition because of the material dispersion. But we can overcome that by using what is known as a waveguide dispersion. Okay. So what we can do is basically engineer the quantum state of the photons coming out. Okay. So for example, we can we can engineer the spectral correlations between the signal and idler photons. So the shape of the joint spectrum of the signal and idler photons coming out typically depends on two things. One is this what is known as the pump envelope function. So that depends on basically what is spectrum of my input pump laser. Okay, so here for example, if you assume like the pump is centered at some frequency omega p naught with some bandwidth sigma p, then you can model it as some Gaussian spectrum like this. And the other is this phase matching function, which depends on this momentum mismatch, right? So this one depends on the energy conservation, omega s plus omega is equal to omega p, and this other phase matching function depends on the momentum conservation or the phase mismatch. Okay, and the joint spectrum is basically a product of these two, and one can basically engineer that again by using the waveguide dimensions because the waveguides are so small that the waveguide dispersion is really strong. So typically, like if you look at the photons coming out of such a waveguide, so you have your pump wavelength here, right? And then the signal and idler photons are symmetrically about the pump, right? So remember, one is slightly higher frequency, one is slightly lower frequency, so they're symmetrically placed about the pump wavelength. So just about the pump wavelength, you get this sort of uh, continuous band here where the photons are generated, and then sort of the generation goes down, and then there's another band which is further away from the pump, okay, and which is much narrower. So in this continuous band around the pump, typically the signal and idler frequencies are correlated, like what sort of we saw in the previous case with lithium niobate, right? So we had seen this correlation in the wavelengths or frequency. So each signal wavelength corresponds to a particular idler wavelength, right? And which we can use, for example, to channelize into different channels for multi-channel, multi-user QKD. So this kind of joint spectrum is not factorizable, right? You cannot write it as some spectrum of the signal times some spectrum of the idler because you have this correlation. But what one can do here in these waveguides is also you can generate another band which is known as discrete band. And here, if you look at the frequency, the joint spectrum of the signal and idler, it looks like it doesn't look like this line here, but it looks more like a blob. Okay. So here you can see that if I take a line cut at any particular IDER wavelength, the projection on the signal wavelength will be the same, no matter where I take this line cut. Okay. So you can basically write this joint spectrum as some spectrum of the signal times some spectrum of the IDER. So this is known as a frequency uncorrelated state. And these are useful for heralded single photon sources. So I detect one of the photons, and then basically that heralds that in the other arm there is a photon present, which I can send further for whatever quantum communication or something. And this kind of source ensures that every photon that is being sent has the same spectrum. Okay. Whereas here, depending on, like for example, if I'm detecting the signal wavelength, then if I detected the signal wavelength here, the corresponding idler photon was here. Let's say for the next pair, the signal wavelength is here, the idler wavelength would be here, right? So the consecutive idler photons won't have the same wavelength. Whereas here, all the idler photons will have the same spectrum every time. So this is important if I want to generate a source which gives out identical photons every time. So remember that was a requirement, for example, when we wanted to do this entanglement swapping and extending the range of the quantum network. Okay, so basically we have these two sort of things we can do with the waveguides. One is this sort of continuous band phase matching, where we have these uh, frequency correlations. Okay, so that typically we use a CW pump, and we can control these sort of the phase matching here by controlling the group velocity and higher order dispersion terms, again, which can be just controlled by the dimensions of the waveguide. And this can be used for sort of frequency and polarization entangled photon pairs. The other one is using a pulse laser and using this discrete band phase matching that I said. So we detect one of the photons and then send the other one as a heralded photon, heralded single photon. So for that, we need this kind of uh, uncorrelated frequency spectrum. And that can be controlled by the group velocities of the pump signal idler photons. Again, which we can sort of just control by the dimensions of the waveguide. So dispersion engineering means basically controlling the dispersion coefficients here uh, using the waveguide dimensions itself. Okay. So there is a certain condition that you need to generate this kind of uncorrelated spectrum here. Okay, it's given by this condition. Basically, what that boils down to is that when you plot this phase matching function, it should come out. The slope should come out to be in the first quadrant. Okay, only then you can get this kind of uncorrelated state. And what we show is that, for example, let's say you take some waveguide with some standard dimensions, height and width here, with some pump input and some waveguide length. You can see that the waveguide dispersion is so strong that by changing the wavelength of the pump, you can change the shape of this phase matching function and also the joint spectrum coming out. So, small video here. You can see as the pump wavelength is changing, this phase matching function is changing. Now it goes into the first quadrant, and you can sort of get this kind of uncorrelated spectrum here. Okay. So this is a very powerful sort of feature of these nano waveguides, that just by controlling the dimensions and the pump wavelength, we can get this different kind of joint spectrum between the signal and IDER, basically engineered to our requirement. So we show different types of spectra at different wavelengths for different applications, and we can also tune the wavelength by tuning the pump. So tune the signal wavelength by tuning the pump wavelength. So a lot of flexible functionality can be achieved just by using this simple waveguide device. Okay, and then we can also generate entangled states. So that what I showed now was the frequency correlations, how we engineer the frequency. But let's say we also want entanglement in the polarization degree of freedom. then we can also generate that. So in the previous case, again, in the lithium niobate uh, waveguide thing, we had to use this Sagnac loop, this loop configuration with clockwise and anti-clockwise path to generate the entangled photons. So we wanted to see that in a single pass, just a single simple waveguide, if we just pump, can we get the entangled photons out directly without any complicated setup outside? Okay. So for that, what we need to do is basically have this process happen for both the horizontal and vertical polarization simultaneously. Okay. So it should happen for both polarizations at the same wavelength simultaneously with equal efficiency, right? Only then can you generate this kind of entangled state. So basically, what we do is uh, we we simulate for different waveguide dimensions, and we see for particular dimensions we can get this phase mismatch, which is the momentum difference between the input and the output. We want that close to zero. So there's this tolerance band here, and the solid and dashed are for the vertical and horizontal. And so we can see for certain dimensions, we can get a broad range of wavelengths where both the horizontal and vertically polarized have close to zero phase mismatch, or basically the momentum matching is happening. So what we did was compute this uh, so-called concurrence, which is like this. It's also a parameter with which you can characterize entanglement, just like the Bell parameter or the fidelity. This concurrence is also another metric. So for a maximally entangled state, the concurrence is 1. Okay. And a concurrence above zero point 0.5 it denotes an entangled state. So here we show that you can get basically almost a perfect entangled state, 98% or above, over a broad range. So zero detuning means like the so pump is at 1550, and then the signal and idler uh, are above and below the pump. So detuning is away from the 1550. So you can see more than 50 nanometers on each side. We can get very high concurrence or good entanglement. We also include the uh, what is known as polarization mode dispersion. So the different horizontal and vertical polarization components, if they travel at different velocities through the waveguide, then they will get separated and then they will become distinguishable, which will reduce your entanglement fidelity, right? So if we include that, there's a range of, you can see that if we use a pump which has small bandwidth, so almost a CW laser, then for even for up to like long waveguide lengths, we can get almost perfect concurrence or perfect entangled state. So, and so basically the idea is to now replace that sort of bulky lithium niobate uh, device with a small silicon chip, which can do the same thing, like generate photons over this broad bandwidth, entangled photons, and then we can channelize them into different channels for multi-user communication. Okay, and then finally, remember that there was also this need for quantum memories to do this sort of quantum repeaters, right? Because we need to store and delay the photons for a certain time. And I said that most of the quantum memories are sort of in the visible range. So, for example, here you can see 606 nanometer or 780 nanometer. So here, one photon, the telecom you send through the fiber network, whereas the other one you send to your quantum memory. Okay. So for this kind of thing, you need sources where you generate. So you generate again this photon pairs, but one of them is in the telecom range and the other one is in the visible range. Right. Also for like hybrid communication schemes. So for example, let's say you want to integrate your fiber network with a free space like satellite communication or some other free space network. For free space networks, typically, again, you want to go to lower wavelengths like 800 nanometer or something. Whereas for fiber, you want to be at 1.5 micron. So again, for these hybrid communication networks, also you need these sources where like one of the photons is near visible wavelengths, whereas the other is at telecom wavelengths. Okay. So again, we showed that one can actually do that with now instead of silicon, with silicon we can't go to visible because silicon has a band gap which is 1.1 micron, so it's not transparent at visible. But if we go to silicon nitride, that's transparent even at visible wavelengths. And with silicon nitride waveguides, we show that you can generate photons here. So again, this is the momentum mismatch. So again, we want to be around zero. So again, so now we pump at a wavelength which is around 1 micron. Okay. So 956.8 here you can see. So this phase mismatch, you can see zero around the pump, then it goes up. It becomes mismatched, but then it comes back down again and it intersects zero somewhere here. So corresponding to the intersection point, you get this peak where photons are generated. So here you can see 700 nanometers and sort of 1500 nanometers. So one is at telecom, the other one is at visible. Okay. And we show that we can also get this PMF angle that we needed for this uh, frequency uncorrelated state. We can also tune that for certain dimensions and pump wavelengths to have that frequency or the spectrally pure states. Okay, and we can tune the signal and idler wavelengths over some wavelength range. You can see here like 700 to 800 for the signal and idler sort of in this telecom wavelength range 1500 to 1600 by tuning the pump wave. Okay, and then not only that, we also showed that we can also get again for sort of typical dimensions that one can make these waveguides. You can get both polarization entanglement and spectral purity. Okay, so again you can get this horizontal and vertical processes both to be phase matched at the same for the same dimension and same wavelength, and you can get this joint spectrum to look like this uncorrelated state which you want for example for quantum memories. uh, okay, so we could get very good entanglement and very high spectral purity both with directly generated out of the waveguide without any complicated setup outside or post processing. Okay, so basically the idea is this: you have some small silicon chip here with some waveguide. You send in an input pump laser at a particular, at some particular wavelength, and out come like these photons, signal and idler. They're entangled with each other in polarization, and one of them you can send to the quantum memory nodes. The other one you can send to the fiber network. Uh, okay, and then one can scale this up so that this has many devices on a single chip for again serving multiple users. So we've also done some first experiments toward this. So we got a silicon chip which was made in this foundry IMEC in Belgium. So we built a waveguide coupling setup, and you can see that it has a lot of components here. So this is a waveguide here, and we couple in and out using optical fibers. So there are some uh, grating couplers here. So the light comes from the optical fiber, then scatters off the grating coupler, and then couples into the waveguide. That's how we couple in and out of these waveguides. And then we've done some four-way mixing experiments. So first classical, where we send like a signal laser also along with our pump laser, and then see the conversion to the idler, just to confirm that this four-way mixing process is happening. And then we also now are doing photon pair generation. So we just send in a pump, and then look for generated photons on either side. And again, we're seeing this kind of frequency correlation. So for example, if the idler wavelength is this one, then the corresponding signal wavelength will be this one. If the idler wavelength is this one, then the corresponding signal wavelength will be this one. So again, this is ongoing work, and then we want to show all the functionalities that I talked about experimentally also. Okay, so I'll end there, and then I just want to thank uh, the whole team behind all this work. So there's this long distance swimmer whose name is Diana Nayat, and so she had written a book about her journey and how she used to train. So I think she was the oldest swimmer to swim solo across the English Channel or something. She has multiple records like that. So you would think that somebody who does a lone sport, right, like just swimming on your own, like I mean, that's like the definition of working alone and achieving things on your own. But if you read that book, she thanks like over 50 people who were on her team who basically are helping her to achieve these things. So there's like a nutritionist, there's a physiotherapist, psychologist, I mean, whatnot. There are like a lot of people helping her out with a lot of things, and without which she cannot really achieve the things, right? So imagine that's for a lone sport. So I mean, all the scientific and technological research that we are doing are all sort of team efforts. So there are multiple people doing this work. I just want to highlight for the work I talked today, the major people who did the work were these PhD students, Shivani and Vikash, who are now graduated and they're now doing postdocs abroad. Shivani is in Germany and Vikash is in the US. Vijay is in the fourth year of his PhD. He's going to complete soon. And also my faculty collaborators at IIT Delhi and also at IIT Madras. So thank you. I'll end there and then now we can have some discussion or questions.
So there are some questions in chat box.
Yeah, so there is one question. How can QKD be integrated into existing classical networks to enable scalable, low latency, and cost-effective end-to-end security? So that's what I sort of tried to talk about today, right? With both these efforts that we are doing. So we want to use the existing fiber networks, right? So again, for that you need some special things like photons have to be at those wavelengths, and then you can take advantage of technologies like WDM. Uh, yeah, that's basically the effort to integrate QKD into existing classical networks. Of course, one challenge would be to separate your sort of classical information uh, from the quantum information, right? So that again you have to separate either on different wavelengths or in different time bins. So people are again looking at different methods to do that, so that classical and quantum information can both coexist on the same fiber. But uh, yeah, and for the waveguide, these are simulation results or actual? Yeah, so the initial results I showed they were all simulation work. So that was just design. We wanted to see if this can be done. And now we are moving on to experiments. So the last few slides were sort of the initial experimental results, but the experiments are still ongoing. And yeah, we have to demonstrate with the chip. We have to demonstrate uh, the field results going forward. Which simulation software can be used for nonlinear phenomena? So typically, I mean, these nonlinear phenomena you can just code up in any numerical software that you use, like MATLAB or Python. Typically, they're just coupled differential equations for the different fields, like the pump, signal, and idler coupled to each other. So you can just use your any numerical software to use to solve the coupled differential equations. To solve for these modes, like I showed you this, like these waveguide modes traveling through the silicon waveguides. So to solve the mode profiles, There are specialized softwares like Lumerical or COMSOL, where you define the waveguide structure and then it will solve the basically the Maxwell's electromagnetic field equations and then tell you what mode propagates the waveguide. And that is helpful because you want to know for what frequency, what is the wave vector and the corresponding effective refractive index. So like these kinds of plots that uh, we are generating these kind of momentum delta beta plots. So that is again using some mode simulation software like Lumerical or COMSOL, where we define the waveguide structure and then it solves for each wavelength, it solves for the mode, and it tells you what is the beta at that wavelength, and then you can calculate the delta beta. Can we use OptiSystem simulation software to design quantum communication system? Uh, so, like you can do a basic analysis like what you do for classical optical communication, right? Like, for example, you can set your wavelengths, link length, etc. But beyond that, I don't think it has the capability to, like, like, for example, if you want to know how much is the loss in your fidelity with distance or uh, all that, I think that there's still, I don't think OptiSystem has the capability for that. Um, so right now it's mostly, I would say, analytical, like analytical simulations or numerical simulation that you write on your own, like in Python or MATLAB that people use. But I think IBM has some, like the IBM Qiskit platform. They have some examples on at least some things I saw, like quantum teleportation and things like that. So you can simulate some, I think, quantum communication links using the IBM. Uh, so there is this IBM online learning platform, I think. Let me just see if I can find the link for that. Then I'll just put it on the chat box. Mm, So there's this one. So I put a link on the chat box. So IBM, here you can see some, so they have modules on QKD, which you can use for simulations. And then one more question, can we use DWDM and design a quantum communication system where signals are spaced at 100? Yeah. So the idea is to use the existing, so for example, for our demonstration, we used 100 gigahertz spacing, right? So one can also try with 50 gigahertz or 25 gigahertz, I think. You just have to use the corresponding DWDM, the arrayed waveguide rating for that. So we had used 100 gigahertz. Uh, where, yeah, they can, I think you can equivalently do with. Actually, for the quantum case, it probably is better to use smaller spacing because then you can get uh, larger, I mean, more number of channels. For the classical communication, because you put data on it, right? And then when you put the data on it, then each wavelength acquires a bandwidth. So now I think nowadays state of the art, you can put like almost 50 gigahertz per channel. So that means there's 100 gigahertz bandwidth already used up for each wavelength. So that's why the wavelength spacings are 100 gigahertz. But for the quantum case, we are not putting any data. We're just sending the single photons on the different wavelength channels. For the quantum, we can actually go down to smaller spacings like 50 gigahertz or 25 gigahertz also. Yeah. So that will enable us to increase the number of channels. So yeah, that's a good question.
Uh, I think, sir, no, there is no question. Okay, sir. Uh, Thank you so much, sir. You and your team have done excellent work in this area, and the session was very informative. Uh, Thank you once again for your kind support and participation in Atal FDP, sir. Thank you so much, sir.
Yeah, thank you. And if anyone, I mean, if they have some questions later or something, feel free to email me or uh, I'll be happy to answer.
Okay, sir. Thank you, sir.
Thank you. Thanks a lot.
Dr. Varun, please stop the recording.